Let's move on to our next unit, that is earth pressure and retaining walls. So when we studied the stability of slopes, there we saw that the soil can keep itself onto a slope up to certain angle of slope and up to certain depth because it has some shear strength. So due to its shear strength, it can sustain itself onto a slope. But what if we increase this angle of slope further? Then this soil mass will simply fall down because in that part the shear stresses will be more. But there are many cases in practical situations where this space is limited. It means that we cannot allow the soil mass to take its shape or to take the slope at which the shear strength is more than the shear stresses. So we need to limit the soil mass. So for that we construct this wall, that is called as retaining wall, and we'll fill the soil behind this wall, and this soil is called as backfill. Now we know that if this wall had not been there, then this soil mass will come down or it will try to fall down. It means that if it is not coming down, then this soil mass is applying some pressure on this wall, and that pressure is called as earth pressure. Now if we are trying to design this wall, so it can sustain this earth pressure. It means that we should know what is going to be the amount of earth pressure that this wall is going to face, so that we can take that into design consideration. So that's why we are trying to find out the earth pressure on the wall. But going further into that, let's see the what is the difference between soil and water. So we know that when we studied the vertical stresses, so if this is the depth z and water table is here, so the vertical stress on the soil will be equal to gamma dash into z, that is submerged unit weight into depth, and vertical stress due to water will be equal to q is equal to gamma w into z, that is simply unit weight of water times the depth of water. Now we know that if this water is stationary, then the pressure distribution in water is hydrostatic. It means that be it vertical direction, horizontal direction or some angular direction, the at any level the pressure due to water is going to remain as gamma w into z. It means that the horizontal pressure due to water, that is sigma x if we denote it with, then that is also equal to gamma w into z. Whereas if it is a soil, then this horizontal stress is a function of vertical stress. It is not simply equal to vertical stress. So it can be written as something k, coefficient k into gamma z. Say that is submerged unit weight. So k gamma dash into z. So here k is the coefficient of earth pressure. So in this case, k, if we write it as k into gamma w into z, so here k is equal to 1. So it means that in case of water, the stresses in all the directions are same, whereas in case of soil, the stresses are not same. So why is it same in case of water and not in case of soil? So the reason again is shear strength. We know that this soil has some shear strength, whereas this water does not have any shear strength. So because of that, in any direction in water, the stresses are remaining same, whereas in case of soil, when we talk about the horizontal stresses, so in that case the shear strength or the shear resistance come into picture, and because of that this horizontal pressure is just a function of vertical pressure. It is not equal to vertical pressure. Now it can be less than the vertical pressure, it can be more than the vertical pressure, depending upon in which direction shear resistance is working. So that we'll understand in some time. So for now we can understand that because of shear strength in soil, the horizontal pressure is a function of vertical pressure, whereas in case of water it is equal to vertical pressure because the water does not have any shear strength. Now we want to understand the, so as I said here that this horizontal pressure, it can be more than vertical pressure, it can be less than vertical pressure. So it is, this thing is there because wall movement takes place. Now we need to understand the effect of wall movement on earth pressure. So when it is going to increase or when it is going to decrease, that we need to understand. So there can be three cases. Let's say this is the wall and this is the backfill, that is soil. So let's we consider it hinged at this point. So after the construction and after filling this backfill, first case can be the wall does not move, does not move at all. Second case can be the wall moves away from soil. And third case can be the wall moves towards the soil. So we'll see when does it happen. So there are three cases. So this wall can be stationary and in its position. It can rotate like this, that is moving away, or it can rotate in this direction, that is moving towards. So there are three cases and there will be three earth pressure coefficients. So let's first understand when the wall does not move at all. So in this case what is happening, we have constructed the wall and this wall and this foundation system, it is rigid. So because of that, this wall after filling this earth or after filling the soil, it does not move in any direction. So if it does not move, that means the lateral strains are 0 because zero displacement is taking place. So if no displacement is there, it means that the lateral strain is 0. Now the earth pressure which is applied by the soil on the wall in this condition is called as the earth pressure at rest. Okay, now this is called as the earth pressure at rest. Now we need to consider two cases. So this diagram shows the earth pressure at rest is this condition. So this vertical axis shows the earth pressure, that is sigma x, and it as a function of wall movement. So when wall moves away, the pressure decreases, or when the wall moves toward the soil, the pressure increases. So that we'll understand in a minute. So first case we saw that when the wall does not move, then the lateral strains are 0 and the pressure in that condition which is applied by the soil on the wall is called as earth pressure at rest. We'll derive the formula for it later, but let's consider the three cases first. So next is the when wall moves away from soil. So this is the wall and we have filled this backfill. Now let's say this wall and this foundation system or whatever the base is there, that system is not rigid. So because of this pressure, the wall moves away. So when it moves away, it will release some pressure because it is moving away, so the soil mass can expand, so the some pressure is released. Okay, so it means that the earth's pressure decreases when wall moves away. So let's understand it further. This is the wall. Now we are saying that it is going something like this. Now because of this is the soil mass. So because of this movement, when this movement takes place, so because of that, a shear plane will form in this soil, and if this shear plane is formed, then the soil mass above the shear plane it will try to move outwards and downwards because this wall is moving here. And the shear resistance we know that it is opposite the direction of movement, so it will be in this direction, that is opposite of wall movement. So here what is happening, here the shear resistance is mobilized. As soon as the wall moves outwards, the shear resistance is mobilized, and that shear resistance is in the opposite direction of wall movement. So the pressure in the horizontal direction, which is there something like this, so the pressure in the horizontal direction, what will happen to it, it will decrease because the shear resistance is in the opposite direction of wall movement, and so this horizontal pressure will decrease. Now how much will it decrease? So we know that after some movement has taken place, so it means that some shear resistance has mobilized. Now if further the wall moves, then further shear resistance will be mobilized, and we will reach a condition where full shear resistance will be mobilized. So after this point, even if the wall moves further, the soil does not have any more resistance. This was the full resistance, let's denote it with tau max. So this was the full resistance that the soil could show. So that was the most or the maximum opposing force. So this resistance is the maximum opposing force that the soil could offer, and at this point this horizontal pressure or the earth pressure, it is minimum, and this minimum earth pressure is called as active earth pressure. So after that, if the wall moves further, the soil does not have any more resistance, so it will simply fall down, this soil mass. So this earth pressure will not decrease further. So this is the minimum lateral pressure. It cannot go below that. So the minimum lateral pressure, this is the minimum pressure which will be applied on this wall. Now the next case is when the wall moves towards the soil mass. So what will happen in this case? Now this is the wall and the soil mass is here. So because of some other structure here, or let's say some stones are there on this other part of the wall, or not stones, some water is stored in this part. So because of this, whatever is there on this other part, this force will be applied on the wall, and because of that it will try to move towards the wall, towards the soil. So that case is what happens in that case, that we'll see. So what happens in this case, this is the wall. So when it tries to move towards, so again a shear plane develops in this soil. Now what is happening, this mass of the soil, it is trying to move upward and outward. So this surface of the soil mass, it will show some shear resistance. So the shear resistance is in the opposite direction of the movement. So the shear resistance now is in this direction. Now we know that in this soil we are talking about these stresses that are in horizontal direction, and these stresses are of compressive nature. Now what is happening, the shear resistance, this shear resistance and these stresses, they are in same direction. It means that if this shear resistance increases, then these horizontal stresses or horizontal pressure, that also increases. Whereas if we compare it with the last time, in case of active earth pressure, so the horizontal stresses were of compressive nature, but the shear resistance was in this direction, or we can say in this opposite direction. It means that when this tau was increasing, the sigma x was decreasing. Whereas in this case, when the tau is increasing, it means when the shear resistance is increasing, then the horizontal pressure is also increasing. Now what will happen? This shear resistance will keep on increasing up to it reaches its maximum resistance, or the maximum shear resistance what the soil can provide, and at that point this horizontal pressure will be maximum. And after that even if the wall moves further, there is no more shear resistance to be provided by the soil. It means that this sigma x will not increase further. Now this in the limiting condition, when this tau has just reached its maximum value, and at that condition what is the value of this sigma x? That is called as passive earth pressure. So here we can see that when the shear resistance is increasing, then this sigma x was also increasing, and in this case when the shear resistance was increasing, this sigma x was decreasing. So this is the thing that we can see from this diagram. When we are talking about active earth pressure, so if we compare it with the earth pressure at rest, so it decreases. Whereas if we talk about the passive earth pressure and compare it with the earth pressure at rest, so it increases. So these are the three cases, and we will see how to derive the formula for that. So let's start with earth pressure at rest. So to derive the earth's pressure at rest, the theory of elasticity is used. The theory of elasticity. So we can use this theory because there is zero displacement. Zero displacement in the soil, and we said that because of that, zero strains or zero lateral strain is there. Now if we consider this is the wall and this is the soil mass behind this, so if we consider an element in the soil that is at depth z below, so the vertical stress is sigma z and horizontal stress from this direction is sigma x, this is sigma z, and if we make a 3D diagram, so this on this face it is sigma x, so in this face we can say it is sigma y. So there are three stresses, and we know that if the sigma x sigma y are at same level, so sigma x is equal to sigma y. Now we can write the strain, but before that some more assumptions which are there in this. So assumptions are that soil is homogeneous, isotropic, and semi-infinite. Semi-infinite means that this depth is limited, whereas the other two values are infinite. And elastic modulus, so we are talking about the elastic theory, so for that elastic modulus and Poisson's ratio, they are taken as, elastic modulus is denoted with E and Poisson's ratio mu is constant for whole soil mass. So now we can write the lateral strain as epsilon x is equal to 1 upon E sigma x minus mu sigma y plus sigma z. Now because in this condition lateral strain is equal to 0, so from that sigma x minus mu sigma y minus mu sigma z is equal to 0. But I said that we know that sigma x is equal to sigma y. It is at the same level. So from that, sigma x is equal to sigma y. So sigma x into 1 minus mu is equal to mu into sigma z. And from here, sigma x is equal to mu upon 1 minus mu sigma z. Now we know that sigma z, it is simply equal to gamma into z, that is unit weight times depth, the vertical stress. So from that, sigma x is equal to mu upon 1 minus mu gamma into z, and this mu upon 1 minus mu, it is denoted as k naught, which is called as Earth's pressure at rest. So from here, sigma x is equal to k naught gamma z, and this sigma z we denoted with P, that is for pressure. So P naught is pressure at rest. So this is the basic formula for Earth's pressure at rest. So this is what we derived, but we considered the assumption was the soil is elastic. But practically if we see, the soil mass is not elastic. So this value of k naught, it is not very reliable. So for that, you can remember this. This will be mostly if nothing is given, and if only Poisson's ratio is given, so then obviously this formula is used. But you can remember some other empirical formulae which were found out using by studying the soil in different conditions. So for this, one more formula is k naught is equal to 1 minus sine phi dash, where phi dash is the effective angle, internal angle of friction. And if it is a normally consolidated clay or normally consolidated soil, so for that k naught is equal to 0.19 plus 0.233 log IP, where IP is the plasticity index, and for over consolidated clay, k naught is equal to k naught for normally consolidated soil times under root OCR, that is over consolidation ratio. So this formula you can remember for the relation between k naught of normally consolidated and k naught for over consolidated. This one is, I don't think you need to remember this. This one is easy, so you can remember this one. So next time we'll see the Rankine earth pressure theory for active pressure and passive pressure.